So we'll talk about energy. We use that word a lot in everyday life. We have energy drinks, and we're trying to conserve energy. What exactly is energy? In science, we define it as the capacity to do work. Well, then we have to know, well, what is work? I mean, we think of work as something you do that you may or may not enjoy, and you get paid money for, right? In science, work is defined as the action of a force through a distance. So we have this illustration of a man pushing a box. If he stands there and just presses on the box but doesn't actually move the box, that's not work. He might be exerting himself, but he's not doing any work. It's the force through a distance. You pedal your bike down the street, you've done work. When you walk, you're doing work because you're exerting a force on your body through a distance. So energy is the capacity to do work. Much like we categorize types of matter, we also categorize energy. We categorize everything. So the two main divisions are kinetic energy and potential energy. Kinetic energy, energy associated with motion. Potential energy associated with position or composition. So in this illustration, we have a 10 kilogram weight teetering at the top of this building. That's unsteady. It's unstable. You give it a little nudge, and we know what's going to happen. It's going to fall, right? This has high potential energy. It is, due to its position, it's high off the ground. If we remove the support underneath it, it will fall. Energy can transform from one kind into another. And so as this weight falls to the ground, its potential energy becomes lower as it gets closer to the ground. But its kinetic energy becomes greater because it's moving faster and faster. Then when it hits the ground, now it has very little potential energy because it's on the ground and it's not moving. So where does all that energy go? Well, it gets dissipated into the surroundings as heat. Heat is a form of thermal energy, a form of kinetic energy. So I talked about the solid state of students, which you guys are in right now. We're sitting in our chairs, but everyone is breathing and everyone is moving a little bit. Thermal energy is the kinetic energy of motion that you have. You're moving even though you're not moving relative to each other. We think of kinetic energy as, well, how fast is it going down the road or something? That's kinetic energy. But sitting in a chair and wiggling, bouncing your knee up and down, tapping on the table, that's also kinetic energy. It's motion. It's just not traveling through distance. So thermal energy, when the temperature of something is warmer, that means the particles are vibrating in place. So a low temperature class of students, you guys are pretty chill right now, right? Everybody's just, sitting here. It's okay. But, after I've lectured for 5.5 hours or something, you get a little antsy, right? Maybe you need to go to the bathroom, or you're just like, you've had it. And people are jiggling. Or maybe there's some really great music on, and people are dancing in their chairs. Okay, that's a higher temperature because it's more kinetic energy. So that's what's going on with the particles. So when this weight hits the ground, it causes the particles in the sidewalk to vibrate, and that increases the temperature of the sidewalk. Now, you may or may not be able to detect it with your hand. If you go and touch the sidewalk, you might not be able to notice the difference in temperature, but that's where the energy goes. So the law of conservation of energy says that energy is neither created nor destroyed. The energy, total energy, is the sum of the kinetic energy and the potential energy. So just like matter that cannot be created or destroyed, energy cannot be created or destroyed. But it can change from one form to another, like from potential energy of being lifted high above the sidewalk to kinetic energy as it's moving faster and faster towards the sidewalk. We can also have energy that flows from one object into another, but the total quantity of energy is constant, and that's going to be an important concept that'll come up in chapter 7. Objects that have high potential energy tend to be unstable. This is true of large objects teetering on the top of a building, and it's also true of some chemicals. Some substances have high potential chemical energy. Chemical potential energy, we say it's due to the composition of the substance, but that really is also due to position, but it's due to position of the individual particles that make up the matter, the electrons and the protons and their proximity and arrangement next to each other. They are charged particles, and so there are electrostatic forces in there. And that's what gives rise to chemical potential energy. Things like gasoline and dynamite have high chemical potential energy. They are unstable. You've got some gasoline, and some of it's vaporized, and you light a spark, and it kaboom, right? It explodes. It's unstable. So in a physical change or in a chemical change, energy is conserved. The total amount of energy in the universe remains the same. Now, it may be distributed very differently, but the total is the same. So systems that have high potential energy tend to change in a direction that lowers their potential energy. Where does the energy go? It goes into the surroundings. So here we have an illustration of a car that runs on gasoline. So we've got gasoline in the tank. Those gasoline molecules are unstable. They have high chemical potential energy. We can react them in the engine of the car, doing a combustion reaction, and cause them to release their energy, and we can use that energy to move the pistons and ultimately to move the car forward. So we've changed the chemical potential energy of the gasoline into kinetic energy of the car. But not all of the energy goes into moving the car. I think we all know that if a car has been on for a while, you should not raise the hood and stick your hand on the engine, right? Why? It's hot. It's going to burn you, right? Where did the heat come from? That's not a design feature of cars. In fact, manufacturers would love it if they could avoid all of that heat. You need a radiator to cool it down. When energy is transformed from the chemical potential energy of the gasoline into kinetic energy, movement of the pistons and of the car, some of it also is dissipated as heat, thermal energy, into the surroundings, and that's why the engine gets hot. So we say there's a loss of energy because it's not 100% efficient. It's not that it's actually lost, it's still in the universe. It's just not useful anymore. And so in processes that use energy, when you talk about efficiency, we're not talking about how much energy gets destroyed in that process or really lost. It's just that it's not useful anymore. So your car burns the gasoline, and out of the exhaust pipe comes the exhaust. That is the combustion products from the combustion of gasoline. Those molecules have much lower chemical potential energy, and they are much more stable. Any questions? Yes?
So anytime you transfer energy from one source to another, do you lose?
Yes. Anytime you transfer energy from one kind to another, you're going to lose the usefulness of some of it. Yeah. And so that's why if you have a process where you're having to transform energy from, do several transformations, that's going to be less efficient than if you have, say, one transformation.
Do you always lose thermal energy?
You always lose it into thermal energy. I think it's probably safe to say that there's always some loss to thermal energy. Yeah. And that's a field of study all of itself.